This is a video on problem solving, which is based on improving improving an idea called a better idea. Basically, it's an improvement or idea-wise improvement, I call it, or idea-wise refinement. Something similar to it. It's not the same as stepwise refinement, which we know of, where we go into small detail of each step in order to. This is a way of problem solving, actually. So here, I will look at that problem which there was error in the initial conception. Okay. Here, now actually the best way to understand this is by an example. The simplest one is we know that square root of a plus b is always less than equal to square root of a plus square root of b. Now, if we try to find out by how much, here the initial thinking would be to add c here, so that square root of b. So, and we also wonder, is there any relationship between the square root of a number and the square of a number? Say a plus b square is equal to a square plus b square plus 2ab. We know this. Is there any such sort of relation here? Here, if we put c here, we will always find that c is nothing but equal to square root of a plus b minus square root of a plus square root of b. But if we change our idea slightly and put c inside the square root and try to find out c such that square root of a plus b plus c equal to square root of a plus square root of b, we will immediately find that c is equal to 2 square root of a times square root of b. So the relationship, the similarity or the symmetry in the relationship between a plus b square equal to a square plus b square plus 2ab can be seen immediately. We have square root of a plus b plus 2 times square root of a square root of b equal to square root of a plus square root of b. So there always does exist some kind of a relationship. We cannot say the similarity or symmetry does not exist. Only thing is we have to see it properly. In other words, we have to change our look. This is the first one. The second one is regarding the problem that are trying to absorb more information into a small space. We know that half and 1 by 4 and 1, all successive halves add up to 1. Now we might be tempted from this to conclude if we take a third of everything as well, 1 by 3, here we have 1 by 2, 1 by 2 square, 1 by 2 cube, and so on, which always adds up to 1. The first temptation would be the same must be true for 1 by 3 as well, 1 by 3, 1 by 3 square, 1 by 3 cube. Of course, if you are slightly mathematical savvy, then you will know that it will not be true. The question is, once you find out if you want to find out why it is not true, then we can refine it. For instance, if we take, the best way to understand this is, if we take half here, half here, half here, and half here, it adds up. But if we take some quantity, say less than half, some ratio r here, we will be, and this is the value 1, we will be left with 1 minus r. So if we wish to use r as the ratio, then if we take r as the ratio, we will be left with 1 minus r, and using r as the ratio of 1 minus r, we will be left with r times 1 minus r. So 1 minus r minus r, so if we take r of 1 minus r, say some value like this, which will be slightly smaller than this, then we will be left with r of taken away r of 1 minus r from 1 minus r, we will be left with 1 minus r square. So we will have to take r of 1 minus r square. So in general, if we, for any ratio r which is less than 1, the equation is actually r plus r times 1 minus r plus r times 1 minus r the whole square plus r times 1 minus r the whole cube, and so on. Now if you compare this with the expression r plus r square plus r cube plus r power 4 plus and so on, you will find these two sums add up only if they add up term wise, they add up. 1 plus r square must be equal to 1 minus r cube must be equal to r times 1 minus r, so r square must be equal to r times 1 minus r cube must be equal to r times 1 minus r square. In other words, r must be equal to 1 minus r always. In other words, 2r must be equal to 1 or r must be equal to half. So this is why only halves add up and not some other ratio when you take a GP series. Now this is the way of improving. Now the problem was, of course, how do we? So this leads us to the solution for the earlier problem that was to try to say code more than a byte in a value which is say maybe a bit or something like that, to try and absorb a byte in a bit. Now I shall look at a simple solution first. It's not necessarily coding it in a byte, but it can bit, but here we have L dash bits here. So, and we wish to code it in L bits, where L dash is significantly larger than L. The idea is simple. If we take we need to determine r such that r power L dash is equal to 2 power L. So r is equal to 2 power L by L dash is true. Now if the ith bit in this, if we take a bits binary number of length L dash, any of the bits could be the starting bit. So the idea here is simple. Since r power I plus 1 is equal to r power I times r, what we do is we scan from the left for the ith bit, which is 1, then set the value of hash to r power I plus r power I times, and code the following string in hash code again, the string k minus 2 power I in r power I times r minus 1. Now there are two things you can do here. Now while coding, since if you wish to say prefer larger numbers to code, then you can use double inversion, which is if the leading bit following bit after this is 0, you can complement it and then try to give preference to 1 here, and having coded it, if this is the new value S2 in which to be coded, take that complement of that complemented key and complement the hash relative to the size of this. This way also you can gain information. So it is to code it recursively. So this will preserve the order also, and it will preserve the okay. So now while coding, you should pass the entire algorithm will be as follows. Hash k v to 0. First step, second, if s greater than or equal to 2, then the first step is set r to s power 1 by L dash. Second step, while k by 2 power I equal to 0, set I to second step is set I to L dash minus 1. Third step, while I to k by 2 power I is equal to 0, set I to I minus 1. We can put set I minus 1. Fourth step would be set k to k minus 2 power I. And the fifth step would be set v to v plus r power I plus hash of k comma I comma r power I times r minus 1. And then finally the third step here would be return v. So this is the entire method. Simple. It is again recursively only. Based on thinking recursively only. You must remember that L dash, what you can do is, if you are coding a string from right to left in order to preserve the order, L dash can be nothing but L plus n. N is that byte here. So you can recursively, you can say try and code it in this, and then add a byte to it, and then try to compress it and try to compress code it in L. Then I can add the next byte. So you can do it byte by byte also, this one. Or you can need not do it byte by byte. You can do it for the entire string as well. Now this is again based on another idea. Of the code trying to code L dash bits in L bits. L dash can be L plus n. Where? So what here we do is, for instance, if this is suited again recursively only. So if these are n bits here, we have r is equal to 2 power L dash by L. So the algorithm for that will be, here what we do is, having determined r, we find the value I such that r power I, largest I such that r power I less than equal to k, and add v to v plus 2 power I, right? So and remove k minus k to k minus r power I, and then if m is the value there, maximum value will also reduce to m minus r power I, and try to again recursively hash this in I bits rather than in L bits initially. So this is also another technique for trying to compress code more, add a little bit excess information and compress it in a smaller space. The algorithm for this will be as follows, which is hash k minus k comma L dash comma L set v to 0 set r to 2 power l dash by l if l equal to 1, then if k greater than or equal to r by 2, set v to 1, then the next step will be set I to floor of binary log of k by l dash, set v to v plus 2 power I set k to k minus r power I and set and 7 set m to m minus r power I eighth step will be set l dash itself to, or set j to ceiling of log m, and then 9 set v to v plus hash of k reduced value of k, reduced value j, which is the reduced length of the key, and reduced length of the hash, which is I, and the 10th step will be return v. So this is a possible way of solving it. This is also another approach. Now the third, now we look at the problem for which the solution, there was a slight error there earlier. We look at that problem now. Now the first thought, when we try to hash a value, the first thought, for instance, we know that hashing by folding is a very popular technique wherein the bits of the key are either folded and added here. Now whenever we try to add like this, we find that order is not preserved. Because of simple reason that if we add two quantities here, due to commutativity law, some value which is less here but increased here for b, the sum would still remain the same even though the number ab itself will be greater than the number a minus c, b minus c as the number. So due to this law, we cannot just always add while both preserving the order as well as invertibility, meaning to be able to recover the data from the first one. So here again, but if we do add and the number is in a base b, if you add 2 digits, the largest value of that will only be 2b. Okay, so now there are two ways. Now we think that simple addition does not work. We have asked why it doesn't work. Because of this law it doesn't work. Now we come and try to see or come up with a way of saying, is there possible to improve upon this basic idea, that of trying to add only but adding it minimally while yet preserving the order, so the growth of the code is slightly small. So what additional facts or any improvement can be made to this basic addition so that it preserves the order. So now what happens is if we have a number of the form d naught b plus d1b plus d naught. Two possibilities. Firstly, the sum d1 plus d naught can be the same. Then two possibilities arise, or three possibilities. We know the law of trichotomy that if you take any two numbers, either one is greater than the other, or one is less than the other, or both of them are equal. Now, since d1 must have a higher weightage over d naught, we could take the sum d1 plus d naught. Now, the value to be added will be close to b only rather than b square. So what we know is if d1 is greater, we could try to code it in the upper half, since that is what must have more weightage. Then we have different values of the sum. So for each value of the sum, for each value of v1, d1, the sum will be the same for up to d1 values only, not more or not less than that. So for those values of d1, and the up can be coded in the based on value of less than b by 2 can be coded on the upper half. I mean lower half, and less than b by 2 and greater than or equal to b by 2 can be coded in the upper half. And then the sum, each of them will be up to d1 only. Within that sum, now if d1 increases by 1, the number of different values increase by d1 plus 1. So the apportioning of the upper area for this could be, say, a fraction of this based again recursively on the sum. Or we could say, when we know the number of values there, we could take only those n values and recursively split it again into 2 for that sum and code it recursively. So the new value that will be there will be only a maximum value will be d1 plus d2, though the sum will be different, can be obtained again differently, and you can apportion it in a different way. So you have to make changes or improvements or refinement based on additional information. So you start with an idea, you see why it fails, you try it out, you see if it works. Most likely it will fail on first glance or on first try or first attempt, it will always fail. Then you ask, why does it fail? So this is the reason. Is there any changes or improvements or refinements that I can make on the idea? If I can make any improvements to the data, so the approach itself or the form itself, or adopt another, perform something else, perform a transformation to improve upon the idea, and then rework the idea, rethink it and rework it and revise the idea and make rectification or changes to it. Finally, when you have done it and it works, you optimize it. In other words, now within this area itself, for different values of the sum, for you apportion it based on the value of d1 alone, but for different values of the sum, again, the apportioning, the size ratio that you take need not always be the sum, because you wish to reduce it, but you can take it in an optimal fashion. So if an idea works, then you improve it. Having improved it, you try to optimize those parameters to get the best possible solution for that particular idea, for that particular approach. So this is another, for which I have not written the complete algorithm, but you can write it quite easily. Now we come back to that other problem. Now what happens here is, if we take, say, again d0 and d1, to a number with 2-digit number, whatever, if you're trying to hash this, say these can be quite large in themselves. All that is required is the value that is added for the least of this, whatever is the value of for d1, must be always equal to and one more than the value that is added for the largest of this. Then order will be always preserved. If your hash value entire for d naught is some we have added it to within s dash less than s, the value that must be added for s d1 must be one more than the value for s. That is all that is required. So this is due to halves only. Now if you try to extend this, like I said, then what, since you are using addition as the means and you wish to do so additively, now what will happen is, if this is the value that you add for the least value of this, and you have split it into parts now. So if you, for this, if you add a certain value, then again for this, the value that you have added is one more than the largest of this value. And the value that you have added for the largest is also one more than this value. So you can now recursively try and solve that problem. Especially if you have coded a value, successfully managed to code a value in n bits, then you wish to incorporate one more byte in the value that you add for the least of this. For the largest, it need not necessarily have to be m times that. It can be slightly only more than that value. It need not be b times m. It can be m plus 1 plus d times something or f of m. So it can increase slightly less than b times m.